So naturally, if we're going to do calculus with multivariable functions, we have to start by defining the limit with a multivariable function. The limit is kind of the heart of all of the other calculus, operations like the derivative and the integral. So naturally, I just want to start by pointing out how it is going to be a lot more complicated to look at a limit in 3 dimensions. Okay, so if we consider what we had to do for a limit in 2 dimensions, so like let's just say x squared when we're approaching x equals 0, right? So if we're looking at the limit as x approaches 0 of x squared, right? So what we would need to do is we would need to look at the limit as x approaches 0 from the left of x squared, and we would need to look at the limit as x approaches 0 from the right of x squared, and we would need to show that they were equal, and that would tell us what the limit was. So we would, this is the point right here at 0, so we would approach from the left, we would approach from the right, and then that tells us what the limit is. So maybe you can already kind of see how that's going to get more complicated here when we have 3 dimensions, right? So if we look at our kind of equivalent function here, let me cut the range off a little bit just to make it easier to work with here, easier to visualize so it's not going off the page here. So if we wanted to look at the limit as xy approaches 0, 0, okay, so that's what the kind of thing we'll need to do here is we'll look at when our 2 independent variables approach a ordered pair. If we just consider the origin here, the 0, 0, well, how many different ways can we approach 0, 0? There's an infinite number of ways, right? We could go along the x-axis, we could go along the y-axis. So that would be more like going down here for the x-axis, going along here for the y-axis, right? We could go in on the side here diagonally, maybe on this side instead, right? There's an infinite number of ways that we could get to that point instead of just the 2. So all of a sudden, it becomes complicated, if not impossible, to really show what some of these limits are. Now, thankfully, in like the case of a well-behaved function like this, it's pretty easy to see graphically that the limit as it approaches the origin is going to be 0, right? So the way we would write this, by the way, so we'll just write this one down since we can see what it is graphically, is we'd say the limit as xy approaches 0, 0 of x squared plus y squared is equal to 0. Okay, and we can do a kind of direct substitution for these kind of well-behaved functions. So things like polynomials or linear functions or whatever, we can still do direct substitution. What's going to be tricky is when we get to the cases where we have 0 over 0, and now we have an infinite number of ways to approach things, right? So we can still put in 0 here, put in 0 here, and then, we're pretty much done. So all of the limit rules that we had in 1 dimension still hold. And all of the so I guess maybe I can just pull that up and we can review that. All the way back in the Math Tool 1 notes. Okay. So like the limit properties, like the limit of a constant, the limit of the sum of 2 functions, the difference of 2 functions, the multiplication, like all these kind of limit laws will still apply in 2 dimensions. Okay. So we don't need to go over all of them again because, they're going to be exactly the same kind of ideas here. So if we go through some examples here of some well-behaved functions where we can just use direct substitution. So let's say we want the limit as xy approaches 2, negative 1 of x squared minus 2xy plus 3y squared minus 4x plus 3y minus 6. Okay, so quite a large function here, but it is a polynomial, so we expect it to be well behaved. When I say well behaved, I mean like it's continuous. It doesn't have any weird like corners or anything like that where things can go wrong. So we'll just go ahead and plug in 2 for x and -1 for y, and we'll see what we get. So we get 2 squared minus 2 times -1 plus 3 times 1 minus 4 times 2 plus 3 times -1 minus 6. And now we have to do arithmetic here, which is always scary, right? So this is where we can make a easy mistake. These will cancel. -8. Looks like we're just going to end up with -6. And I do have the answer here. And that does look correct, -6. Okay, so we just go ahead and do direct substitution, and it's pretty straightforward, right? You know, we have a lot more arithmetic to do now because we have multiple variables to account for, so naturally the functions are going to be more complicated, but nothing we can't handle. So another example here, if we do the limit as xy approaches to -1 of, let's say, 2x plus 3y over 4x minus 3y. Okay, so we have a quotient function, top and bottom, both polynomials here, linear functions in fact. So again, we can take the limit of the top and the limit of the bottom. So we just have to basically, again, just do direct substitution, just plug the numbers in. So it's going to be 2 times 2 plus 3 times -1 over 4 times 2 minus 3 times -1. So we're going to have 4 minus 3 over 8 plus 3. So we get 1/11. Okay. All right, so now let's look at some ones where it gets more complicated. Okay. So for these more complicated ones, it's almost always going to be easier to show that it doesn't exist. It might even be impossible to show that it does exist. So the limit as xy approaches 0, 0 of 2xy over 3x squared plus y squared. Okay, so when we do direct substitution, what happens here is we get 0 over 0. So that doesn't tell us anything. So now we have to rely on a different approach. So when we ran into 0 over 0 in single variable calculus, what we would do is ideally we would use L'Hopital's rule, right? So 2 problems with L'Hopital's rule. 1, we don't know how to even define a derivative with 2 variables, but 2, there is no L'Hopital's rule for 2 variables. Okay, I say there is no L'Hopital's rule. There is forms of L'Hopital's rule under certain conditions, but it's actually still kind of an area of active research, which tells you it's not nearly as straightforward as it is in single variable calculus. But if you just Google like L'Hopital's rule for multiple variables, you'll find recent papers on it. Like I just did it right before this video, and one of the first results was a paper from 2020, right? So it's still being studied, different forms of that. All that to say, not something we're going to use right now, right? So then we would maybe look for an algebraic way to simplify the function. And that's not going to work here at all, right? We can see, you know, there's really nothing we can do with this. Like there's no kind of factoring that we can do or anything like that. So we're really pretty limited here. So what we want to do is we want to start approaching this from different sides. So in this case, if the limit does exist, there's going to be basically no way for us to actually definitively say it does exist, because again, there's an infinite number of ways we can approach the limit with these 3 dimensions. So we're really hoping that it doesn't exist, and that there will be a way for us to show that. So basically what we need to do is, out of those infinite number of ways to approach the origin, we need to show that at least two of them are not equal to each other. So we want to approach it from two different directions and show that they're not the same. And if they are the same, then we want to consider a third direction, see if that one's the same. So we're going to try different approaches. Okay, so it's not just the left and right like it was with single variable, right, in 2 dimensions. So we'll try different approaches. Okay. I don't know why I wrote that so badly. Okay. So let's consider approaching. So let's approach along y equals 0. So in other words, the x-axis, right? So this is a pretty natural way to approach it. So if we're on the x-axis, that means that y is equal to 0, right? So what we do here is we think about the function on the x-axis. So this would be f of x 0, which is going to be, it's just going to be 0 if you plug in 0 for y, right? You have 0 divided by 3x squared, so 0. So the limit as x, we would say x0 approaches 0, 0 of f of x, y. So here we put in 0 for y. Okay, let me make it clear that this is the x-axis. Is going to be equal to 0 because this is just a constant now, right? So when we take the limit of a constant, we just get that constant, which is 0. So if we're going along the x-axis, the limit looks like it's 0. So that would be analogous to like coming in from the right or left or something like that in single variable calculus. And we'll look at the graph of this after we do it mathematically here. So let's approach now along the y-axis. So these are kind of the typical first two choices. Okay, so the y-axis here. So f of 0 y is also equal to 0 because we have 2xy on the top, right? So this isn't going to help us too much, but I just want to write it down anyway because sometimes it will. So it's a good one to remember. Of f of xy, so the limit of 0y approaches 0, 0 is going to be equal to 0. So coming in from the x and the y-axis, they do look the same. So two of the approaches are equivalent, but that's not enough for this. So maybe we try a different approach. So maybe we can try approaching along the line y equals x. Okay. So this is like a diagonal line through the origin. So it goes through the origin. So that's basically what we're looking for, is because we're looking at approaching the origin, we're looking at all the different lines that go through the origin, right? So the x-axis does, the y-axis does, y equals x does. Again, there's an infinite number of lines that do. So if we're looking at if we're looking at the line y equals x, then these are going to be the same thing, right? So we're going to replace all of the y's with x's. Or you could do it the other way. It wouldn't matter. 3x squared plus x squared, because that was a y. So this is going to be 2x squared over 4x squared, which is 1/2. Okay. So that tells us that the limit, as we would say xx approaches 0, 0 of f of xy is equal to 1/2. Okay, so coming in from the x-axis at 0, coming in from the y-axis at 0, coming in from the line y equals x, it's 1/2. So now we have two approaches that are not the same. So this tells us that the limit does not exist. Okay. Which is best case scenario for us here if we're trying to just do this problem algebraically. Because if it did exist, then theoretically we'd have to show every single line that you could come in on, would have the same limit, and there's an infinite number of those, so that would be impossible. So let's go ahead and, look at this one graphically. So this was 2xy divided by 3x squared plus y squared. Okay. I think this is not correct. Maybe I need to put the times in here. Yeah. Okay, so I got to put the times in there manually. So this is what the function looks like. So you can definitely see how it gets kind of weird at the origin. Even not really being familiar with multivariable functions yet, you can still kind of see that things are getting weird there. There's like this big dip right there, right? So you can see here's the origin here. So if we're coming in, let's kind of orient ourselves here. So coming in from the y-axis was the one we did second, actually. There it looks like the limit is 0. It's really hard to tell, with the graph being three-dimensional here. Then coming in from the x-axis, which is this one, it was 0. So then we did y equals x, which would be a diagonal line here, and that's where we get the 1/2. Okay. So again, really not easy to tell. There's really no good way for me to kind of show this here, but regardless, we saw the math, so we don't really need to see it graphically, but I just want to show that we can see why this is a problem point. Okay. Okay, so we'll do one more example here. So let's look at the graph of it first this time. So this is going to be the function 4x times y squared divided by, need the whole thing divided by here, divided by x squared plus 3y to the 4th. I think that all went in the exponent. Got to be really careful about how type it in on this thing. Okay, so that all looks correct. So 4xy squared over x squared plus 3y to the 4th. So yeah, definitely getting weird around 0. Okay. So we'll look at, what the limit algebraically says it is there. But we're hoping that it just doesn't exist at all. Okay. Because then that means that we have a chance to show that. So we want to look again at the limit as it goes to the origin. Okay. So then we want to consider any approach which would pass through the origin. So if we do direct substitution, we're going to get 0 over 0. If you do if you do the y-axis or the x-axis, it's definitely going to be 0, right? Because the numerators are both have an x and a y in them again. So if you set one of them to 0, they're going to be 0. So let's just go right for y equals x. Okay. So we'll do the limit as x approaches 0, 0 of 4x times x squared over x squared plus 3x to the 4th. So this is the limit as x approaches 0, 0 of 4x to the 3rd over can't combine this one, so x squared 3x to the 4th. So we can cancel some x's out here, so you can cancel an x squared out of everything basically. So this is going to be The limit, I'll just write limit, so I don't have to write it over and over again here. 4x over 1 plus 3x squared. Okay. So now when we plug in 0, 0, we're just going to get 0 over 1, which is still going to be 0. Okay. So this one didn't help us either this time. So now we have to look for a different approach. And we just kind of got to keep doing it until we find a better one. So we could try a different line. Like we could try approaching along the line y equals 2x, for example. But that's not going to help us in this one. So let's go right for y equals x squared. Okay. So let's see what happens with this one. So that does pass through the origin, so it's fine to consider. So we have x squared goes to 0, 0 of, this is going to be 4x x squared over x squared plus 3 x squared to the 4th. Okay. So again, I'll just write limit here. So this is x to the 4th. So this is 4x to the 5th over x squared plus 3x to the 8th. Okay. And I think we're going to just run into the same problem here, right? Because we're going to cancel some x's. This is going to be 4x cubed on top over 1 plus 3x squared. So this is still going to be 0. Okay. So we need another approach. And it can be kind of hard to come up with them after a while. One that does work here is now we could try x equals y squared. Okay, so we can try, this is still like a parabola. It's just parameterized a little bit differently here. This would be like a sideways parabola if we were looking at it as a single variable function. So we have the limit as y squared y approaches 0, 0 of 4y squared over y squared plus 3y to the 4th. Okay. So you can maybe start to see why this one is going to work a little better. Because we have 4y to the 4th, and now on this one, this is y to the 4th plus 3y to the 4th, so we have 4y to the 4th. Okay, so these are going to cancel, and we're just going to have 1. So we're doing the limit of 1, which is equal to 1. Okay, so it can be tricky to find the right approach if if you're just kind of searching. I kind of just start at the less complex ones and kind of build up here. So I guess this is the order I would go through, right? The x-axis, the y-axis, y equals x squared. Maybe try turning it around into x equals y squared, which happened to work in this case. So here we get the limit is 1. All the other limits were 0. So therefore, they're not the same on every single approach. So therefore, the limit does not exist.